Welcome to this video. In this video we will see how to transform data. We're going to start by dragging the iris dataset, which is a dataset we already have explored visually in previous videos. And when we check the scatter plots, we could see quite clearly that there were correlations among the data, especially among the A3 and A4 attributes, also A1 and A3. But there are some clear linear correlations among some of the features of this dataset. If we compute the correlation matrix, we'll be able to quantify those correlations that we saw visually, and we'll see that correlations go up to 0.96, and there are two pairs of components with correlation around 0.8. So there is redundancy in this data. This data, however, it really only has 4 attributes and we have 150 instances. So we should be fine working with all the 4 attributes because we don't really have that many attributes for the number of instances. That said, we're going to apply anyway a dimensionality reduction transformation, which is called PCA, Principal Component Analysis. So we're going to drag the PCA operator to the output port of the correlation matrix. The example output of the operators is the original data. So the original iris dataset goes into correlation matrix, and the same data comes out of these ports and it will go to principal component analysis. In PCA, we're going to compute a rotation of the feature space, and the rotation is going to be in such a way that the first rotated axis is going to try to capture as much variance as possible of the original data, and the second axis will capture as much possible variance among the one which is left, discounting the fair axis, and so on. We can quantify that variance in each axis, and that variance is often used as proxy for information. If something has absolutely no variance, if I have a set of patients for which all of them the gender equals female, that attribute, if it's the same for every single patient, has no value in my analysis. We would like attributes which have at least some variance in order for them to be useful, and typically, not always, but typically the more variance an attribute has, the more information it's providing. By default, PCA is going to try to preserve 95% of the original variance, and we're going to see what's the result of the transformation here. If we run the process, what we see here is each of the 4 transformed components created from the original 4 attributes, the standard deviation and the proportion of the variance they are capturing. So the first principal component is capturing already 92.5% of the variance of the data, 92.5% of the information, we hope, although it's not always the same variance as information. The second one is adding another 5.3%, and we already rise to 97.8%. The third one adds another 1.7%, going to 99.5%, and the last one just adds 0.005%. So if we want to capture 95%, that was the setting in the operator, we just need the first 2 components, because with the second one we already go to 97.8%. If we want to see what exactly these projections are, we can go here to eigenvectors, and this is explaining me how the rotation was done. It's telling me that the first principal component is 0.3 multiplied by the attribute A1 minus 0.82 multiplied by A2 plus 0.857 multiplied by A3, and so on. So this is the rotation matrix of my transformation. And in this last plot over here, I can see how much variance do I have with 0 components, 0 variance, 0 information, with a single one, with 2, and so on. If we output, well, we already have here the output of the data. This is the iris dataset after applying PCA, only keeping the first and the second component, only keeping these 2 components, because in the design of the operator I'm asking just for 95% of the variance. If I compute a correlation matrix on that output components, on the transform components, I'll see that this second correlation matrix has 0 values of correlation among the components, because Pca is built in such a way that each component is orthogonal to the previous one. If I go back to the sign and I ask for 98% of the variance instead 95, I rerun the process. Now, well, I'm seeing the correlation matrix is already showing me that I have 3 components, and if I go to the data, I can see that I have 3 components instead 2 components, because in this case I need to go up to the 3rd component to reach 98% of the information. It's really providing me already 99.5% of the information. And if I'm willing to lose 10% of the variance, then I could do that with a single component. I will get just a single component. Let's go back to the design, and we're going to apply Pca again over a dataset that we already explored visually previously. I'm going to remove the iris dataset source. I'm going to look for the operator which enables me to load WCA files, the ARFF format, and I'm going to configure it to load one of the files that I have provided with the course. It is within the classification folder, and it was the Wisconsin database breast cancer dataset. In this dataset, we did have a class, a label, which is not going to be recognized by RapidMiner unless I explicitly indicate that one of the attributes is not a regular attribute but is the class. So we're going to use the set role operator. Here is mostly important, so Pca will ignore that operator. That operator is called class, and the role is label. So if I apply the same setting, let's reset Pca to the standard variance 95%. If I run this process, surprisingly, I only have a single component according to the second correlation matrix. And if I check the data, indeed see I have a single component. And Pca is telling me that with that single component I'm already capturing 98.2% of the variance. This is completely shocking, because originally I have 30 attributes in these datasets. Let's explore the original data before the Pca transformation. This original output port in Pca, or in general in any operator, will provide the unmodified data. The iris data enters the example input port of the Pca, and the data after the Pca transformation will output the example port, but the original data without any Pca transformation will be available in the original output port. And if we check this dataset, we're going to see that we have 569 instances, examples, according to the nomenclature of RapidMiner, and I have 30 attributes. Having 30 attributes, that's way too many attributes for just 500 instances. 30 squared 900. But it's a little bit shocking that with a single component, according to Pca, I'm able to capture 98.2% of the original data. Something fun is going on here. Let's check the eigenvectors. This is the values of the 30 rotated axes. However, just the first one seems to be capturing 98%, over 98% of the variance. I'm going to sort the different components of the first principal component. And when I'm sorting, I'm checking that the first component is 0.852 multiplied by the attribute 24 plus 0.517 multiplied by the attribute 4. And these values are very close to 0, a few values almost 0, and then the vast majority, 20 something of the attributes are multiplied by 0. So this is telling me that this first component is just the attribute 24 and the attribute 4. Like the other 28 attributes are providing pretty much no information or no information. What's going on here? Let's check the original data and let's see what's happening with the attribute 24. I'm going to compute statistics. I'm going to go down to the attribute 24. And if you look at 24, you see that the minimum value is 185 and the maximum is 4000. Compare this, for example, with the attribute 25, where the minimum value is 0.07 and the maximum 0.2. Or the 26, where the minimum is close to 0 and the maximum is close to 1. Variance here is huge compared with most of the attributes. The variance for 24 and also for number 4, although smaller, the variance here goes to from 143 to 2500. Variance for these attributes is way larger. And in principal component analysis, we are using variance as a proxy for information. This is the issue we discussed in the theoretical sessions of comparing houses and dollars or euros for measuring wealth of persons. In the Euclidean space, having one more euro in your bank account, it is the same change as owning one more house. However, in the real world, one more house gives you a significant amount of wealth, one more euro, pretty much nothing. And we have discussed that one way of addressing this issue is normalizing the data. I'm looking for the normalize operator, and I'm going to drop the normalize operator before computing the correlations, which are not really going to be affected by normalization, and before computing the principal component analysis. After normalizing, variance in all the axes is going to be more comparable. We're going to normalize the number of houses and the number of euros in the bank account, and there won't be such disparities when computing variances over both axes. And now, if we check what is the number of principal components that we need in order to get 95% of the variance, we see that we need 10 components. This is more believable. This is already a really significant decrease in the dimensionality in the feature space. We went down from 30 to 10 components, and according to PCA, this should be capturing at least 95% of the data. It's quite a good result, and 10 squared is 100. 100 is below the number of instances, so we should be fine to move from this point onwards. This example has been designed to teach you and to make more emphasis, because we already discussed this in the theoretical session, of the importance of normalizing data before applying PCA. In the case of the iris dataset, we did not need the normalization, because in that case all the attributes have the same meaning. They are the length and the width of the sepals and petals of the iris flowers, and all of them are just a few centimeters. We don't have very different things in the different axes of our feature space. We don't have attributes with very different meanings, such as one house, 1 euro. You may want to save this setup at this point. Well, I'm going to save it just to reflect how this is doing. Save process, and I'm going to call the process PCA. I'm going to start with a new blank process. I'm going to drag again the iris dataset, and we're going to apply some other feature transformations that we cover in the theoretical sessions. For example, discretization. Discretized by binning is the discretization of equal width bins. For example, if I ask for 3 different bins, I'm going to get 3 labels per attribute, whose meaning could more or less be small, medium, large. So if I run this process, I compute the statistics, I'll see that for each attribute I have 3 different labels. Their meaning will be kind of small, medium, large. So I move from the metric attributes to label attributes. In the case of A3 and A4, which have more like a normal distribution, the binning seems to yield more or less the same number of instances for each of the labels, but that's not the case for A1 and A2. Instead, discretizing with equal with bin, what here is going to happen is that we're going to, for each attribute, subtract the minimum from the maximum and divide it by 3, because I have asked for 3 bins, and that will be the width of each bin. Instead, discretizing by binning, I may discretize with frequency. I get the original data out of the original output port of the first discretize operator. I'm going to connect it here. And this discretization, I'm also going to ask for 3 bins. It will attempt to create bins with constant density of instances. We're going to change the width of the bin, but we would like to have more or less the same density of instances in each of the bins. If I check now the histograms for the first 2 features, which were the one who had way different densities in the first case, now they are more homogeneous. In practice, they typically are not exactly the same number of instances, because in the end I need to discretize at some point the access, and in that point there may be more than 1 instance, and they either go to the bin on the left or the bin on the right, so I may not manage to achieve perfect density, constant density in each of the bins, but it's a more homogeneous discretization than it was in the previous case. Here you can see that there is no huge imbalances between the 3 labels for each of the attributes. Another transformation that we saw is numerization, which is pretty much the opposite as discretization. Let's go to the golf dataset, and let's look for the nominal. Well, by the way, when discretizing, binning is how RapidMiner calls it, you have an additional option which is discretized by user specification. If you know how to discretize a certain feature, such as for example the age of the patient, and you know certain ranges which are relevant for your problem, you may use that operator. The nominal to numerical operator, it will change all the labels in your dataset by numbers. So we move from having, for example, a nominal attribute outlook, which could take the values rain, overcast, and sunny, to having 3 different binary attributes: outlook equal rainy, outlook equals overcast, outlook equals sunny, where 0 and 1 is showing, for example, that for this golf game there was no rain, there was no sun, it was overcast. And the same is happening here for width equals true and width equals false. Regarding discretization and numerization, it's always very useful to keep in mind what type of data can my technique work with. There are some techniques which can only work with metric, numeric data, neural networks for example. There are some techniques which can only work with labels, decision trees for example. There are other techniques which can manage both type of data, for example Bayesian techniques. Sometimes you may feed nominal data to a technique which can only handle metric data to a neural network, and RapidMiner may just run the process. That means that somehow RapidMiner has numerized that nominal data. How was that numerization made, and is that numerization the best to your problem? Those are things to keep in mind, because maybe you can numerize better than the automatic way that RapidMiner will use for numerization. And the same goes for discretization. If you are using a decision tree, your metric data has been discretized somehow, and maybe that discretization is not the best one for your problem. I'm going to remove all the operators. I'm going to leave the iris data, and going to use one last operator to transform features, which is the generate attributes. And this is a very generic, versatile operator, where here we can create mathematical functions. For example, we're going to create new attribute, and here by clicking in this small calculator I can create mathematical formulas. For example, I can say that the new attribute is going to be A1 multiplied by A2 minus the, for example, I'm going to go to mathematical functions and I'm going to compute the logarithm in base 10 of A3 minus some trigonometric function, the sin of A4. This feature of course has absolutely no meaning, as just showing you that you could build any type of mathematical expression using this operator. You may use this to manually create some nonlinear transformation of your data in order to try to come up with a linear partition of data which was initially not separable by linear partitions. You could add here as many new attributes as you want and create the formulas. And now if we run it, we're going to have the new attribute. We have now a modified iris dataset with the 4 original attributes plus the new attribute we have added here. We go back to the designer, and the very last thing we're going to do is sample the data. This is not really attribute transformation, it's sample instance transformation. The sample operator, the standard one, it will allow you to randomly choose a subset of the data. For example, here we're going to choose 100 instances out of the original 150. If I type here probability and I type here, for example, 0.5, I'm going to choose 50% of my original samples. So if I run this process, I'm going to get, instead the 150 instances, 66 instances, approximately half of the original instances. I can sample with replacement. The sample operator is sampling without replacement. With replacement, the sampling operator with replacement is called bootstrapping in RapidMiner. In this case, instead removing each sample and choosing from the original dataset from the sample, instead choosing it and removing it, I'm copying it to the other sample. So if I sample with replacement, I may ask for 500 samples from the iris dataset, because I'm going to copy the instances and I can go over 150. If I run the process, now I get a sample set of 500. Of course, most of the samples are just copies. For example, you can see here these 5 instances, which seems to be a copy of the same original instance. Typically, this is used when you are really starved of data and you want to artificially try to increase the amount of the data you have for training or for testing. The stratified, well, if we run this, if we go back to these results and we compute the statistics and I check the label, you see that right now the labels do not have exactly the same value for all the different 3 species. They more or less have the same value because it's random sampling and I start with 1/3 proportions for each of the 3 different species of iris flowers, but I don't have exactly the same number of instances. You want to make sure that after sampling you are preserving exactly the same proportions for each of the different classes involved in the problem. You may use stratified sampling. In stratified sampling, it will sample in such a way that the original proportions of the classes are maintained. So here, if we check, we see how we sack exactly the same number of each of the 3 species of iris flowers. Sampling, as we'll see later in the course, is important for especially training supervised models, where we want to use a different set of data for the training stage and another set for validating how good that model it is. It can also be helpful when working with very large data sets, because for computational efficiency point of view, for computational reasons, because we don't want the analysis, especially initial fast exploratory analysis, to get some feeling of how the data is behaving. We don't want that process to be slow, and if we have millions of hundreds of thousands of data points, I may want to just subsample a few tens of thousands and work faster with that data, to explore the data a little bit, to get some feeling of the issues, to get some feelings of which techniques may work better or worse with my data, before running the actual analysis, which may take hours for the models to train. So that's everything for this video. See you on the next video.